Okay, so now that we have our batch of input that we'd like to feed into a transformer, let's start basically feeding this into neural networks. Now we're going to start off with the simplest possible neural network, which in the case of language modeling, in my opinion, is the bigram language model. And we've covered the bigram language model in my Make More series in a lot of depth. And so here I'm going to sort of go faster, and let's just implement the PyTorch module directly that implements the bigram language model. So I'm importing the PyTorch NN module for reproducibility. And then here I'm constructing a bigram language model, which is a subclass of NN module. And then I'm calling it, and I'm passing in the inputs and the targets. And I'm just printing. Now when the inputs and targets come here, you see that I'm just taking the index, the inputs x here, which I renamed to IDX, and I'm just passing them into this token embedding table. So what's going on here is that here in the constructor, we are creating a token embedding table, and it is of size vocab size by vocab size. And we're using nn.embedding, which is a very thin wrapper around basically a tensor of shape vocab size by vocab size. And what's happening here is that when we pass IDX here, every single integer in our input is going to refer to this embedding table and is going to pluck out a row of that embedding table corresponding to its index. So 24 here will go into the embedding table and will pluck out the 24th row. And then 43 will go here and pluck out the 43rd row, etc. And then PyTorch is going to arrange all of this into a batch by time by channel tensor. In this case, batch is 4, time is 8, and C, which is the channels, is vocab size, or 65. And so we're just going to pluck out all those rows, arrange them in a B by T by C, and now we're going to interpret this as the logits, which are basically the scores for the next character in a sequence. And so what's happening here is we are predicting what comes next based on just the individual identity of a single token. And you can do that because, currently the tokens are not talking to each other, and they're not seeing any context except for they're just seeing themselves. So I'm a token number 5, and then I can actually make pretty decent predictions about what comes next just by knowing that I'm token 5, because some characters follow other characters in typical scenarios. So we saw a lot of this in a lot more depth in the Make More series. And here, if I just run this, then we currently get the predictions, the scores, the logits for every one of the 4x8 positions. Now that we've made predictions about what comes next, we'd like to evaluate the loss function. And so in Make More series, we saw that a good way to measure a loss, or like a quality of the predictions, is to use the negative log likelihood loss, which is also implemented in PyTorch under the name cross entropy. So what we'd like to do here is loss is the cross entropy on the predictions and the targets. And so this measures the quality of the logits with respect to the targets. In other words, we have the identity of the next character. So how well are we predicting the next character based on the logits? And intuitively, the correct dimension of logits, depending on whatever the target is, should have a very high number. And all the other dimensions should be a very low number. Right? Now, the issue is that this won't actually, this is what we want. We want to basically output the logits and the loss. This is what we want, but unfortunately, this won't actually run. We get an error message. But intuitively, we want to measure this. Now, when we go to the PyTorch cross-entropy documentation here, we're trying to call the cross entropy in its functional form. So that means we don't have to create like a module for it. But here when we go to the documentation, you have to look into the details of how PyTorch expects these inputs. And basically the issue here is PyTorch expects, if you have multi-dimensional input, which we do because we have a B by T by C tensor, then it actually really wants the channels to be the second dimension here. So if you So basically, it wants a B by C by T instead of a B by T by C. And so it's just the details of how PyTorch treats these kinds of inputs. And so we don't actually want to deal with that. So what we're going to do instead is we need to basically reshape our logits. So here's what I like to do. I like to basically give names to the dimensions. So logits.shape is B by T by C, and unpack those numbers. And then let's say that logits equals logits.view. And we want it to be a B times T by C, so just a two-dimensional array, right? So we're going to take all of these positions here, and we're going to stretch them out in a one-dimensional sequence and preserve the channel dimension as the second dimension. So we're just kind of like stretching out the array so it's two-dimensional, and in that case it's going to better conform to what PyTorch sort of expects in its dimensions. Now we have to do the same to targets, because currently targets are of shape b by t, and we want it to be just b times t, so one-dimensional. Now alternatively you could always still just do -1, because PyTorch will guess what this should be if you want to lay it out, but let me just be explicit and say b times t. Once we've reshaped this, it will match the cross entropy case, and then we should be able to evaluate our loss. Okay, so that ran now, and we can do loss. And so currently we see that the loss is 4.87. Now, because we have 65 possible vocabulary elements, we can actually guess at what the loss should be. And in particular, we covered negative log likelihood in a lot of detail. We are expecting log, or ln, of 1 over 65 and negative of that. So we're expecting the loss to be about 4.17, but we're getting 4.87. And so that's telling us that the initial predictions are not super diffuse. They've got a little bit of entropy, and so we're guessing wrong. Yes, but actually we are able to evaluate the loss. Okay, so now that we can evaluate the quality of the model on some data, we'd like to also be able to generate from the model. So let's do the generation. Now I'm going to go again a little bit faster here because I covered all of this already in previous videos. So here's a generate function for the model. So we take the same kind of input, IDX here. And basically, this is the current context of some characters in some batch. So it's also b by t, and the job of generate is to basically take this b by t and extend it to be b by t plus 1, plus 2, plus 3, and so it's just basically, it continues the generation in all the batch dimensions in the time dimension. So that's its job, and it will do that for max new tokens. So you can see here on the bottom, there's going to be some stuff here, but on the bottom, whatever is predicted is concatenated on top of the previous IDX along the first dimension, which is the time dimension, to create a b by t plus 1. So that becomes the new IDX. So the job of generate is to take a b by t and make it a b by t plus 1, plus 2, plus 3, as many as we want max new tokens. So this is the generation from the model. Now inside the generation, what are we doing? We're taking the current indices, we're getting the predictions. So we get, those are in the logits, and then the loss here is going to be ignored because we're not using that, and we have no targets that are sort of ground truth targets that we're going to be comparing with. Then once we get the logits, we are only focusing on the last step. So instead of a b by t by c, we're going to pluck out the -1, the last element in the time dimension, because those are the predictions for what comes next. So that gives us the logits, which we then convert to probabilities via softmax. And then we use torch.multinomial multinomial to sample from those probabilities. And we ask PyTorch to give us one sample. And so IDX next will become a b by 1, because in each one of the batch dimensions, we're going to have a single prediction for what comes next. So this num samples equals 1 will make this be a 1. And then we're going to take those integers that come from the sampling process, according to the probability distribution given here, and those integers get concatenated on top of the current sort of like running stream of integers. And this gives us a b by t plus 1. And then we can return that. Now, one thing here is, you see how I'm calling self of IDX, which will end up going to the forward function. I'm not providing any targets. So currently this would give an error because targets is sort of like not given. So targets has to be optional. So targets is none by default. And then if targets is none, then there's no loss to create. So it's just loss is none. But else, all of this happens and we can create a loss. So this will make it so if we have the targets, we provide them and get a loss. If we have no targets, we'll just get the logits. So this here will generate from the model. Let's take that for a ride now. Oops. So I have another code chunk here, which will generate for the model, from the model. And okay, this is kind of crazy. So maybe let me let me break this down. So these are the IDX, right? I'm creating a batch will be just one, time will be just one. So I'm creating a little 1x1 tensor, and it's holding a 0. And the D type, the data type, is integer. So 0 is going to be how we kick off the generation. And remember that 0 is the element standing for a new line character. So it's kind of like a reasonable thing to feed in as the very first character in a sequence to be the new line. So it's going to be IDX, which we're going to feed in here. Then we're going to ask for 100 tokens. And then n.generate will continue that. Now, because generate works on the level of batches, we then have to index into the 0th row to basically unblock the single batch dimension that exists. And then that gives us a time steps, just a one-dimensional array of all the indices, which we will convert to simple Python list from PyTorch tensor, so that can feed into our decode function and convert those integers into text. So let me bring this back, and we're generating 100 tokens. Let's run. And here's the generation that we achieved. So obviously it's garbage, and the reason it's garbage is because this is a totally random model. So next up, we're going to want to train this model. Now, one more thing I wanted to point out here is this function is written to be general, but it's kind of like ridiculous right now because we're feeding in all this, we're building out this context, and we're concatenating it all, and we're always feeding it all into the model. But that's kind of ridiculous because this is just a simple bigram model. So to make, for example, this prediction about k, we only needed this w. But actually what we fed into the model is we fed the entire sequence. And then we only looked at the very last piece and predicted k. So the only reason I'm writing it in this way is because right now this is a bigram model, but I'd like to keep this function fixed, and I'd like it to work later when our characters actually basically look further in the history. And so right now the history is not used, so this looks silly, but eventually the history will be used. And so that's why we want to do it this way. So just a quick comment on that. So now we see that this is random. So let's train the model so it becomes a bit less random. Okay, let's now train the model. So first what I'm going to do is I'm going to create a PyTorch optimization object. So here we are using the optimizer Adam W. Now in the Make More series, we've only ever used stochastic gradient descent, the simplest possible optimizer, which you can get using the SGD instead. But I want to use Adam, which is a much more advanced and popular optimizer, and it works extremely well. For typical good setting for the learning rate is roughly 3e-4, but for very, very small networks, like is the case here, you can get away with much, much higher learning rates, 1e-3 or even higher probably. But let me create the optimizer object, which will basically take the gradients and update the parameters using the gradients. And then here, our batch size up above was only 4. So let me actually use something bigger, let's say 32. And then for some number of steps, we are sampling a new batch of data. We're evaluating the loss. We're zeroing out all the gradients from the previous step, getting the gradients for all the parameters, and then using those gradients to update our parameters. So typical training loop as we saw in the Make More series. So let me now run this for, say, 100 iterations, and let's see what kind of losses we're going to get. So we started around 4.7, and now we're getting down to like 4.6, 4.5, etc. So the optimization is definitely happening, but let's sort of try to increase the number of iterations and only print at the end, because we probably want to train for longer. Okay, so we're down to 3.6 roughly. Roughly down to 3. This is the most janky optimization. Okay, it's working. Let's just do 10,000. And then from here, we want to copy this. And hopefully, we're going to get something reasonable. And of course, it's not going to be Shakespeare from a bigram model, but at least we see that the loss is improving. And hopefully, we're expecting something a bit more reasonable. Okay, so we're down at about 2.5-ish. Let's see what we get. Okay, well, dramatic improvement certainly on what we had here. So let me just increase the number of tokens. Okay, so we see that we're starting to get something at least like reasonable-ish. Certainly not Shakespeare, but the model is making progress. So that is the simplest possible model. So now what I'd like to do is, obviously this is a very simple model because the tokens are not talking to each other. So given the previous context of whatever was generated, we're only looking at the very last character to make the predictions about what comes next. So now these tokens have to start talking to each other and figuring out what is in the context so that they can make better predictions for what comes next. And this is how we're going to kick off the transformer. Okay, so next